We're going to look at evaluating limits of rational functions as x approaches a finite number. When evaluating limits, a key thing to remember is that evaluating the limit as x approaches a of f of x is easy if f is continuous at a. It is easy by definition of continuity. Remember that if a function is continuous at a, then the limit as x approaches a of f of x is equal to f of a. So that tells us that we can evaluate the limit by simply plugging a into the function if we know a function is continuous at a point. This means that evaluating the limit of a polynomial is really easy because polynomials are continuous everywhere, and so everywhere for a polynomial the limit as x approaches a of the polynomial p of x is just equal to p of a. Nothing more to talk about polynomials. The limits of rational functions, which are ratios of polynomials, rational functions, are easy if a is in the domain of r of x. If a is in the domain, then the limit as x approaches a of r of x is equal to r of a. So that means most of the interesting stuff about evaluating limits of rational functions happens when a is not in the domain. So we're going to look at this rational function, r of x equals x squared minus 5x plus 6 over x to the fourth minus 9x squared. We're going to look at these 5 different limits, and over the course of looking at these 5 limits, we're going to build this flow chart that will be helpful in evaluating limits of rational functions. Eventually, you'll just do all these things automatically, but when you're first learning, it definitely helps to have a little direction. So let's start with this idea that rational functions are continuous everywhere in their domain. So the first thing we want to do is think about what is the domain of r of x. Well, it will be where, in a rational function, the domain is wherever the denominator is not 0. So we want to see where is x to the fourth minus 9x squared equal to 0. And we can figure that out by factoring. And x squared comes out. We've got x squared minus 9 left. We can factor that. X minus 3, x plus 3. So the denominator of r of x is equal to 0 when x equals 0, x equals 3, or x equals negative 3. So the domain is all reals except for 0, 3, and negative 3. Okay, so let's remember that. That's going to be helpful as we move on to our first limit. All right, so if we want the limit as x approaches 1 of r of x, the first question we need to ask ourselves is 1 in the domain? And, well, on the last slide, we said that everything was in the domain of r except for 0, negative 3, and 3. So the answer is yes, and that makes us happy because that means it's easy to evaluate the function. Its limit is just equal to r of 1, and so we plug in 1 to this function, 1 squared minus 5 plus 6 over 1 to the fourth minus 9 times 1, and we get negative 4 plus 6 is 2 on top, negative 8 on bottom, so the limit is negative 1/4. 1 down. Let's start thinking about how our flowchart works with that problem. So the question we asked to begin was, is A in the domain of R? And in this case, our answer was yes. So we just said, then the limit as x approaches a of r of x is r of a. And an example of that would be a function like this that looks like a polynomial. All right, time for problem number 2. We want to look at the limit as x approaches 2 of r of x. So our first question, is 2 in the domain of r? Yes. That's in the domain, so that makes us happy again. We're just going to plug in 2. Now notice plugging in 2 here, is going to be a little bit harder than plugging in 1. So let's try factoring. The top factors to x minus 3, x minus 2, and we had factored previously, this could, the bottom, it could be x squared times x minus 3, x plus 3. So notice if we plug in 2 up here, that top is just going to be 0, and the bottom will be 4 times 2 minus 3, which is negative 1, times 2 plus 3 is 5. So we have 0 over negative 20, which is just 0. So the limit as x goes to 2 of r of x is just 0. Notice the 0 on the top of a rational function is not a problem. A function 0 divided by 20 is 0. All right, so we're not going to add anything new to our flowchart on that. That was exactly the same situation as the last one. X was approaching a number in the domain, so we just plugged it into the rational function. We needed to do a little more algebra to simplify our work, but essentially that was the same type of problem as the first one. Okay, so here things get interesting, because now we've got the limit as x approaches 3. And 3 was not in the domain of R. So we're not just going to be able to plug in and see what happens. Notice that if we were to plug in, we plug in a 3 there and 3 there, so we would get the top approaching 0 and the bottom approaching 0. This is a 0 over 0 indeterminate form. In a rational function, where the factor that makes the top 0 is the same as the factor that makes the bottom 0, those cross out, and so we can write the function differently. We can say x minus 2 over x squared times x plus 3. Now we've got a function that is identical to the original function at every point except 3. This new one is defined at 3. So we better, if we really want it to be equal to r of x, we've got to say x is not equal to 3, so that we keep the same domain that the original function had. But when we take a limit doesn't depend on the value of the function at the value we're approaching. It only depends on the value near, the values near that value we're approaching. So we can take the limit of this function as x approaches 3, and it will be equal to the limit of r of x as x approaches 3. So we say this is going to be equal to the limit as x goes to 3 of this new function. This new function has 3 in its domain, and it's still a rational function, so the limit is going to be equal to what we get when we plug in 3, which is 3 minus 2 over 3 squared times 3 plus 3. That's 1 over 9 times 6, which is 1 over 54. So the limit as x goes to 3 of r of x. Okay, so let's look at our flowchart. And is a in the domain of R? We got no as our answer. And we asked, does plugging a into R of x result in an indeterminate form? Or we saw that plugging it in did result in an indeterminate form. And the answer there was yes. So what we did was we found a simpler function by factoring, such that the new function f of x was equal to r of x everywhere but at x equals a, and then we simply evaluated the new limit, the value of the function, that new function, and said that'll be equal to the limit we were interested in. That situation where two functions are equal everywhere except a single point is a hole. So an example of that would be this. Our next problem is to look at the limit as x heads to 0 of r of x. And we've got our r of x simplified down to this expression with the added condition that x can't be equal to 3. It doesn't really matter to us in this case that x can't be equal to 3. We're only looking near 0. Let's think about what's happening to both the top and bottom as x heads to 0. Unlike in the last case, the top is not also heading to 0. And that means we're going to have to do something different because we don't have an indeterminate form. The top is heading to -2 as the bottom heads to 0. This is not indeterminate. We know it's going to be huge, either huge positive or huge negative. So when we're approaching a non-zero number in the numerator and a 0 in the denominator, we can have any of three situations. So x is heading to 0. We could have the expression heading to positive infinity on both sides of 0. We could have the expression heading to negative infinity on both sides of a or 0. Or we could have a situation where one side is heading towards positive infinity and the other side is heading towards negative infinity. In this first case where both are heading towards positive infinity, we would write the limit equals infinity. It doesn't really equal infinity, but we're saying the limit fails to exist because it heads towards infinity. In this case, we'd write negative infinity as our answer, and in this case, we'd write does not exist because the two one-sided limits are completely different. So in this situation, the thing that's important is what the sign of our infinity is on each side of a. A in this case is 0. So in this case, when we have x heading towards a number that's not in the domain, but the form is not indeterminate, we need to look at the two one-sided limits to see whether the two sides are both heading to the same infinity or they're heading to different infinities. And that's going to depend on the signs of the numerator and the denominator. And those could be different on the two sides. So limit as x heads to 0 from the right of x minus 2 over x squared times x plus 3. Well, the top, as x heads to 0 from either side, is definitely going to be negative because when we're close to 0, the -2 is going to dominate. So the top is going to -2. This expression, when x is heading to 0, is heading towards 3. This expression, when x is heading towards 0 from the left, we're putting in a tiny little negative number, like -0.00001, and squaring it. So that becomes something we're going to write sacrilegiously as +0. Just for thinking about what's going on here, we have -2 times +0 times +3. So we have negative, positive, positive. So this whole thing is going to be equal to negative infinity. And if I do the limit as x goes to 0 from the right, x squared x plus 3. The top is still going to head to -2. This is still going to head to 3. This time, what we plug in for x is a very small positive number, like 0.00001. We square it, so we still get a +0. So in this case, we have -2, top's heading to -2, the bottom's heading towards +0, and +3. So again, we have negative, positive, positive. So overall, we've got negative infinity. And since the two one-sided limits are both negative infinity, it's a situation like this. And the two-sided limit we say is negative infinity, which is shorthand for the limit fails to exist because r of x approaches negative infinity or grows without bound in the negative direction. Okay, so on our flow chart, this time we had, does plugging a into r of x result in an indeterminate form? No, it didn't. So what we first did was to do a sign analysis of the two one-sided limits. Look at the limit as x goes to 0 from the right and the limit as x goes to 0 from the left to figure out whether each of those was positive or negative infinity. And then we asked, are those two limits equal? And in this case, the answer was yes. So the limit, the two-sided limit, was equal to the two one-sided limits. In our case, it was negative infinity in our case, but it could be either negative infinity or positive infinity. the example 1 here is an example where both one-sided limits were positive. All right, so we've got one more case left to consider, and that's where those two one-sided limits turn out to be different. So that's what we're going to see here in number 5. So the limit as x goes to -3. So the limit as x goes to 3 of r of x, we've got to look at what happens on the top. The top is going to head towards -3 minus -2 is -5. The bottom is going to head towards -3 squared, which is +9. And then we've got this x plus 3, which is going to head towards 0. And the question then comes down to what is happening as we come in from the left to -3, and then as we come in to the right from -3. We know in this case that each of those one-sided limits is going to be either positive infinity or negative infinity because we've got non-zero on top, 0 on bottom. So that's going to tend to explode in one direction or the other. So we've already got that -5 and 9. Those two do not depend on whether we're approaching -3 from the left or the right. But this expression does depend on whether we're approaching from the left or the right. Here, if I'm approaching -3 from the left, that means I'm plugging in a number that's a little bit smaller than -3, like -3.00001. And if I do -3.001 plus 3, I'm going to have a number that's very close to 0, but negative. So notice I'm not putting equals as I write this. This over here is just notation to help me think through what's going on. It is not equal to that limit. But what we have here is negative, and then positive, and then negative of something that we know is blowing up. So this limit is 2 negatives and a positive. That's going to blow up to positive infinity. And on the other side, the limit as x goes to -3 from the right, x minus 2, x squared, x plus 3, again, that's going to head towards -5, which is just going to be a negative number. X squared is going to head towards 9. That's going to be a positive number. But this time, as I plug in something slightly to the right of -3, like -2.9999999, when I add -2.999 to 3, I get something very close to 0, but positive. So what we have here is negative over positive times positive. So this whole expression heads to negative infinity. We've got two one-sided limits which are different. So the two-sided limit is going to not exist. So the limit as x goes to -3 of r of x does not exist. And we can finish out then our flow chart with this place where the two one-sided limits are not equal, and so we just say the two-sided limit doesn't exist. It's an example of that. We see positive infinity on one side and negative infinity on the other. So there we've got everything that can happen as we evaluate a limit as x approaches a finite value a if r is a rational function. We've looked at all the possibilities. And let's just finish up by taking a look at what the graph of this might sort of look like. We don't know everything about it, but we can make some good headway. R of 1 is -1/4, so we've got a point sort of like here. R of 2 we had found was 0. The limit as x goes to 3 was 1/54, but remember we had a hole there, so there's a tiny little hole somewhere like this. And then the limit as x went to 0 on both sides was negative infinity. So we have something like this. We don't know what else happens, but something like that. And then the limit as x goes to -3 from the left was negative infinity. So over here we have something like this. We have something like this, and as x goes to -3 from the right, we have something like this. Now, as we learn more calculus, we can start to figure out more pieces of this function. But for right now, let's just take a look on Desmos. There we have it. Point come in there. There's our point heading towards positive infinity. Here, now we head back towards negative infinity. Over here, come from negative infinity up to 2, that's 0. And then we head out here, and as x gets to 3, that point completely disappears. If we look at another function, this function f, which is exactly similar to r except for that one missing point, let's do this approach to 3 again, but instead of just looking at the r function, there we see f of x, our function that's exactly the same, but with those x minus 3's crossed out. We see the coordinates right there are exactly the same. Okay. As we let a approach 3, okay, they're the same at 2, the same at 2, 2.7. Whoops, I went too far. The f function still exists there. That's 3 and 1/54, I guess. But the r function doesn't exist. We're in the whole of the r function. So that is that.